By golly, what do we have here? Here are 16 lamps. They're undergoing an accelerated life test. They've been manufactured under some kinds of experimental conditions, and we're submitting them to an environment which is far more severe than anything they would likely receive in actual use. And we're going to study their life. We want to determine when these lamps expire. Now, the quality control people have collected data of this kind for a long period indeed, and we can see what the distribution of lamp lives has been for this accelerated life test using their historical records. And we see the distribution of lamp lives over here. Some of the lamps, you'll notice, expire about 1,000 hours, and some of them sort of hang on up here around 1,500 or 1,600 hours, but not very many. We have a skewed distribution, a tendency towards long life. And you'll notice that this distribution has a mean of 1,200 hours. And the quality control people have determined the variance of these individual lamps, and it turns out the variance is 10,000 hours squared. Incidentally, gang, that's a skewed distribution, and if we had plotted the frequencies against the log of time, that would have been very normal indeed. But we're going to use the data in terms of the initial metric, life in hours. Well, what do you say we record the essential characteristics of this distribution over here on our lamps, so we have it for ready reference. You'll recall now that the mean was 1,200 hours, and that the variance of the individual lamps is 10,000 hours squared. Okay, and now we'll have to wait around until these lamps die out. So I suggest we see if we can accelerate time a bit. I will start recording some of the essential data, which is relative to these lamps, and we'll thereupon see what we can do about speeding up time. By golly, that final one went out. And if I tally the life here and sum these blooming things up, the average comes out 1,250 hours. The average life of these 16 lamps turned out to be 1,250 hours, and I shouldn't really ever record an average without at the same time telling you the number of observations which make up the average. It was, in this instance, 16. Okay, what do you say we discuss a situation in which we could have obtained data of this kind and see how we would analyze such data? I want you to imagine the following scene. An engineer has a bright idea about how he can extend the mean life of the lamps without, he feels, changing any lamp characteristics and without modifying the cost of the process. And he brings his idea to the plant manager, and who's impressed by its originality and its possibilities, and he, signs the necessary requisitions, and the guy runs off with the money and time and facilities and so forth to try out his ideas. We get a sample of the lamps and we test them and so forth, and the average comes out 1,250. Now, you can all guess what would happen if that average had come out, say, 1,100. He would have written a report, and that would have taken care of that. No one would have worried about whether or not he had improved the mean life performance of the lamps. Had the average come out 1,100, the mean is already 1,200. But we've got an average of 1,250, and this is, rather interesting information. You notice the average is on one side of the mean in this instance. And so the young engineer is very enthusiastic about his results. He says, see, by golly, I have improved the mean performance of these lamps. But the manager's been around a while, and he says, well, now, observations vary, and averages vary, therefore, and, it is possible that you could get an average of 1,250 hours, even though the mean was still 1,200. What we're getting involved in here is something called a one-tailed test of significance. We really want to find out whether that average 1250 is so distant from the mean as to disenchant us of the belief that the mean is still 1200 hours. And so we end up doing what is called a one-tailed test of hypothesis. Well, what do you say we go to the board and put up some of the arithmetic and so forth associated with this particular problem? Now, you'll remember that the average turned out to be 1250 hours, and that it was based on 16 observations, and that the variance of this process, the variance of the individual lamp lives, had been determined to be 10,000 hours squared, 10 to the 4th hours squared, and that the objective of the experiments is to improve lamp life. We're interested here in a one-tailed test of hypothesis. The null hypothesis, the sponsoring hypothesis, if you will, is that the mean is still at 1200 hours. And the alternative hypothesis, the hypothesis against which we're testing the null hypothesis, is that the mean is greater than 1200 hours. We're doing a one-sided test. It's a one-sided alternative. We could have perhaps cooked up an example in which the one-sided alternative was that the mean was less than eta sub 0. But here's our problem. We're worried about this particular alternative hypothesis. Okay, now we're dealing with averages and so forth. And what's the reference distribution for averages? And you're all supposed to correspond. The reference distribution for averages is a normal distribution with a mean eta and with variance sigma squared over n. The reference distribution for averages, the essential statistic in this particular analysis, is a normal distribution with mean eta and variance sigma squared over n. And we sometimes abbreviate this statement, make it a little bit more terse, by writing it in this fashion. The averages are normally distributed with a mean eta and with variance sigma squared over n. Well, now that we've locked our statistic into a distribution, the normal distribution, that immediately brings to mind the normal deviate. And so what do you say we put up the normal deviate and see what happens in this case? The normal deviate for our particular problem is z is equal to the average, y bar, minus the hypothesized value of the mean, divided down by the square root of the variance of the average, which is sigma squared, the variance of the observations, divided by n. And if I plug in the appropriate numbers, the average was 1250, the null hypothesis is 1200, down here is the variance, 10 to the 4th hours squared, 16 observations, and perform that calculation, it turns out that z, the normal deviate, comes out to be 2. And now the important question is this an unusual value of z? Now you'll remember we're doing a one-tailed test of significance. And so the trick is, what value of z is it that leaves 5% in the one tail of the curve? Well, we can all see a picture of the geometry involved in this particular case. Here we see the distribution of the normal deviate. Its mean is 0. And you'll notice out there at 1.64, that's the value of z which leaves 5% in the tail of the curve. Now, pray, gang, what value of z did we obtain? We obtained a value of z equal to 2. So, gee whiz, that's a rare event z. And then what, therefore, does that do towards, with our attitude towards the hypothesis that the mean is 1200 hours? And our attitude towards that hypothesis is scorn, scorn. We reject the hypothesis. We dismiss it from our mind's eye. It's really very good news, because that's what the man has been saying. He says, I have increased, you see, the mean performance of the lamps. And indeed, it seems that you could not have gotten reasonably an average of 1250 hours if, in fact, the mean of the process was still 1200. So the data testify in favor of the alternative hypothesis. We are able to reject the null hypothesis using this one-tail test. Just about this time, the plant manager says, yes, but we said that we could increase the mean performance of the lamps without upsetting any of the other lamp characteristics. He said, now you remember, these are 60-watt lamps. We sell these lamps for 60-watt lamps. And I don't want to see the wattage of those lamps being less than 60 or more than 60. And what is the average wattage of these lamps? You notice now we're worried lest the average be too low or too high. And as a consequence, we get ourselves locked into a situation where we're dealing with a two-tailed test of significance. Well, it turned out in this case that the average wattage for these lamps was 61 watts. That was based, of course, on the 16 observations. And a quick conference with the quality control people tell us that the variance of individual lamps of this wattage is approximately 4 watts squared. Now recall, we want to maintain the wattage, and we'd be distressed if we saw the lamps go too low or too high from their legally set level of 60 watts. And so we're interested in a two-tail test. Now, the null hypothesis in this case, the originating hypothesis, is that the mean is 60 watts. And what would be the alternative hypothesis, gang? The alternative hypothesis is that the mean is not equal to 60 watts. You see, that the alternative is that it's just not equal to eta 0. I don't care whether eta 0 is greater or less, or eta A, the alternative hypothesis, greater or less than eta 0. Either way, you see, it's a two-sided test. Well, once again, the reference distribution for our averages is a normal distribution, and this would bring me to a computation of the normal deviate. Here's the normal deviate once again. Z is equal to the average minus the null hypothesized value for the mean divided down by the square root of the variance of the average. If I plug in the data, y bar was 61, and the null mean is 60, and the variance was 4, and n is 16. And if you go through that calculation, it comes out, once again, z equals 2. R. Now we have the important question, is this an unusual value of z? Now remember, we're doing a two-tailed test of hypothesis. Okay? What's the value of z that leaves 2.5% in this tail and 2.5% in that tail of the distribution? Well, we'll see a picture of the distribution right here. And you'll notice that the critical value of z is plus 1.96 and minus 1.96, so that the total area in the tails of the curve is 5%. Incidentally, it's interesting to read that statement across the top there. It says the probability that we'll find a value of z between the limits minus 1.96 and plus 1.96, the total probability there is equal to 95%. Well, now, to return to our problem, what value of z did we observe? We observed a value of z equal to 2. What's the critical value of z? The critical value of z is 1.96. So our z is a rare event z. And so what do we do about the hypothesis that the mean of these lamps is still 60 watts? We reject it. That's disappointing news in this case. Of course, this would stimulate people to do further experiments. They'd try to figure out, now what the devil can we do to hold on to our gain in mean life and keep the wattage at 60? The thing about tests of hypotheses are they give you a yes or no answer. It's a sort of an elementary decision-making technique. Really what we're interested in this instance is to learn more about the process. For example, what is the real mean of the process, the new process we're talking about? Do you think the mean is 1,250? You know, bang, to the guys that say the mean is 1,250. It's not 1,250. The average is 1,250. The average is a statistic that we have, you know, carpentered out of those varying observations and so forth. It is the best estimate of the mean, but the mean isn't equal to 1,250. It's the best guess.